Hello everyone, and welcome to Stories on the Rooftop. We're delighted to have you here with us today, and wherever you are, we hope that you are keeping safe and well. My name is Sabrina Nanji. I'm the team member for Stories on the Rooftop, which is part of the arts and culture portfolio of the Aga Khan Youth and Sports Board. Stories on the Rooftop is a platform for sharing personal experiences and engaging in open dialogue with each other. Through these conversations, we seek to enhance our understanding of the diversity of experiences within our community, whilst also connecting with each other to discuss issues that are relevant to all of us. I'm delighted that today Farah Alibay will be our speaker and will take us through her experiences of being a systems engineer at NASA's Jet Propulsion Laboratory for the past 6 years, and also her experiences of being a flight system engineer on the Mars 2020 team, the rover mission scheduled to land on the Red Planet in February 2021. With that, I'd now like to ask Farah to begin. Thank you, Farah, and over to you.
So good evening, everyone. I'm in Los Angeles, so it's lunchtime here. My name is Farah Alibay, and as was mentioned, I work at the Jet Propulsion Lab here in Pasadena, California. JPL is one of the many NASA centers in the United States, and I've been here for about 6.5 years. And in that time, I've actually worked on 3 Mars missions. So I'll be talking a little bit to you today about my journey, how I got here, kind of what sparked my interest into aerospace and how I ended up all the way in California. And then I'm going to talk a little bit about the current mission that I'm working on, which is the Perseverance rover. And Perseverance is actually just about halfway to Mars right now. We launched on July 31st of this year, and we are landing February 18 of 2021. So we're getting close. And so I'll talk to you a little bit about some of the work I did on the team, and then looking forward to what's going to be happening in the next few months, so that you can follow along to my journey over those next few months. Okay, so here's a little bit of a montage of where I come from and who I am and how I've grown up and ended up here. So on the left here, you can see me as Minnie Mouse. I was probably about 4 or 5 years old. So I grew up in Quebec, and I grew up just outside of Montreal. I was born in Montreal and then grew up in a small town outside of Quebec. And Quebec, and being from Canada, our national sport, our national pastime is skating. And so you are not Canadian if you don't either figure skate or play hockey in the winter. So I picked figure skating, and this is sort of my first figure skating show. But all that to say that I grew up in a French-speaking community where my family was one of the only minorities there. So I grew up being surrounded by people that didn't really look like me, and I didn't really have role models of people that I could look up to that had a similar journey to mine, or that my parents had had. My parents were born in Madagascar. They immigrated to Canada in the 70s and 80s. So I had a very different upbringing, perhaps, than some of my peers. Now, I was lucky enough that we had a community in my family in Montreal that we would go see fairly often, and I got to adapt and also learn to live within a predominantly white community, and took the best out of that community too. And so it was a different upbringing, but it was definitely very rewarding to have those two. So I lived there until I was 13, and then my family moved to Manchester when I was in year 9. So if you can imagine, I don't know if any of you are about that age, but I was in year 9. I didn't really speak English all that much, and then I got taken away from my friends and moved all the way to England. At the time, I thought that was a terrible idea, but I'm so thankful that my parents made that change and moved to England, because it allowed me to learn English. It also allowed me to just learn something new, learn a new culture, learn a different way of doing things. And so that second picture you can see there, in the presentation is a picture from year 13, just before going off to university, and those are my friends at Loretto Grammar School. So I did my GCSEs and A levels in Manchester, and then I went off to the University of Cambridge, where I did undergrad and masters in aerospace engineering. And so a little bit of a story of how I ended up there. People always ask me, why did you go do aerospace engineering? What was it that you were passionate about? And honestly, I just really liked space. Like growing up, I had a lot of toys, and I liked Star Wars and Star Trek. And I grew up in the '90s, so that was really big back then, and still is now, I guess. And there was a movie at the time that came out called Apollo 13, which recounted the journey and the story of the Apollo 13 astronauts. That there was an incident on the way to to the moon, and the astronauts here on Earth, in Houston, helped them and brought them back safely. So if you've ever heard the line, "Houston, we have a problem," that's where it comes from. It's that particular event. And so, I remember watching that movie and just being fascinated by astronauts in space and thinking like, wow, isn't that cool that all of these people work together to make these amazing accomplishments, right? And I think at the time I didn't really actually realize that could be a job, partially because it was in Houston all the way, it was so far away in my mind. Well, none of these people really looked like me. But once I was in school, especially during my A-levels, I was really good at math and physics. And I'm not kidding, one day in year 12, we do these little career tests. And so I did, this little online test. And then all of a sudden, the top career choice for me was aerospace engineer. And I was like, what? Like, this is a real job? And I think it hadn't really clicked until then that, whatever your passion is could also become a job. And I think it clicked at about that moment. But it wasn't without hurdle. I also remember when I made that decision that I think aerospace engineering is what I wanted to do. At the time, I was also thinking like, oh, maybe I could be a doctor. Like that sounds like something that would be really good for me as well. I remember having a chat with, you have careers advisors and talking to them about what I wanted to do. And the lady who was my careers advisor was like, well, engineering is a really male-dominated field. I don't know if you're going to succeed there. And that is, it's still incredible to me that someone said that to me. And me being me at the time, I was like, what? I will show you. I'll become an engineer. And that's how I ended up applying at the University of Cambridge. But I always tell this story because whatever your career path might be, wherever you might be, that there's going to be those hurdles along the way. There's going to be people that won't believe in you. But the importance is that you have to remember that you only need one yes, one acceptance, and you have to believe in yourself and make your own journey. Because at the end of the day, there's always going to be people who are going to tell you to do something different, to not follow your dream, and those people, just don't listen to them. If there's something that you want to do, in this case, this is what I was passionate about, go after it. The worst that can happen is that you can fail and try again. But if you don't try in the first place, you're never going to get there. And it was true for applying to University of Cambridge too. I had backup schools and I decided to apply to Cambridge because I thought, wouldn't it be cool to go there? And I got in, right? And it didn't harm to try, and it worked out for me. But one of the challenges when I was at Cambridge was that in the UK, at least at the time, when you did something in aerospace, it was really focused on the aero side of it. And in fact, I was working on jet engines, and that's what I did my master's thesis on, which was really cool. Don't get me wrong, right? Like I got to collaborate with Rolls-Royce and understand how jet engine works for different types of planes. And that's really, really fun, but it wasn't quite what my passion was. I still had sort of this desire to go work in space specifically and explore the solar system. I was particularly interested in planetary exploration, not just Earth orbiting space. So around that time when I was finishing my master's degree, I got an offer to go do a PhD at MIT, which is Massachusetts Institute of Technology, which is out in Boston. And, at the time my parents lived in England, my brother was in England, my family was in Canada, and I had a job offer in England. But I knew in my heart that that's something that I wanted to try and pursue. And so I thought, at the time I was 22, I thought, you know what, I'm just going to go for it and take this big risk and move to a brand new place and try it out, right? And I think I went in with the thinking of, well, I already have a good degree, I have a good education, let me go try this out. There's no reason, I had nothing tying me down yet. Let me go try something a little bit crazy, figure out if I can do this PhD thing, one of the biggest tech schools in the world. If I fail, that's okay, I'll just come home, right? But if I succeed, that's a door to something I've dreamed about since I was a kid. So I took the hop, moved across the pond again, moved to Boston. Thankfully, I was used to the weather. It's very similar to Montreal, so that wasn't too bad. And I ended up doing my PhD there. And during that time, I actually ended up doing 2 internships here at JPL, which is how I got my foot in the door. And actually, my first summer here at JPL is when we landed the Curiosity rover, which is up until now the biggest rover that we landed on Mars. So that was pretty incredible to see. And I got to see the team that worked on that and thought, wow, isn't it so cool that this team is coming together to land this massive rover on another planet? And I thought that's really what I wanted to do. So I came back for a second internship, and again, right, along those lines of you have to make your own story, you have to open your own doors. I remember in that second internship, I took the opportunity that summer to literally knock on every single manager's the door, and ask for a job. So every single manager that could possibly hire me, I was knocking on that door, telling them what I could do, telling them what my skills were, and asking them for a job. And again, it was one of those moments where I was like, well, this is what I want. I really have nothing to lose here. Let me go ask, because again, if I hadn't tried, I think I would have kicked myself for the rest of my life, because this is really what I wanted to do. But that's, again, something that I like sharing, because it's kind of a reminder that things don't just fall into your lap. Things don't just happen because you want, because you dream about them. You have to put in the work, and you have to knock on doors, and you have to ask for help. And so I knocked on those doors. I relied on those allies and those mentors that I built up along with that time, and they helped me get that job. And so I started at JPL out here in California back in 2014. And the first mission that I worked on was a small CubeSat mission. And those are very small spacecraft that went to Mars. And I'll show you a couple pictures of that in a second. But that's this picture here of me being young and bright-eyed. And then, as I mentioned, I've worked on a few Mars missions since then, and the latest one being Perseverance. So I mentioned that the first mission that I worked on was this pair of CubeSats. They were called Marco, Mars Cube 1. So they're kind of like big cereal box-sized spacecraft that we launched from Earth, and they co-launched with a mission called InSight that I also worked on. And here's a picture of InSight. And what they did is they did telecommunication relay for InSight as it was landing on Mars. So when InSight landed on Mars, it was sending signal back of what was happening. And these little cube boxes were sending that information back to Earth. And that was the first time that spacecraft of that size had gone interplanetary and performed their tasks. So it was really cool. It was a really small team, and completely different really from the big missions that we do at JPL, but it was really fun to be in a small kind of scrappy environment and building these things. Literally my blood, sweat, and tears went into those spacecraft. I also worked, JPL works in a variety of missions. We specialize in planetary exploration as a whole. So these missions here in the middle are small and bigger missions that I worked on more in the early proposal phase, because one of the parts of my job that I get to do is I get to dream up of missions. I get to dream up with the scientists of design a spacecraft that could achieve their goals and then propose those to NASA. They don't all go through, but this one here is a set of small spacecraft that will be studying coronal mass ejections from the sun. So the sun sometimes has these storms that we want to observe because they have implications for the safety of astronauts or even for our safety here on Earth. And that's a mission that it was me and a scientist in a room that came up with that concept, and then it became a proposal, and now it's a real mission. So it's a cool aspect of my job too, that I get to sort of dream up things and then go to NASA and ask for money to make those happen. But the biggest mission that I worked after that was InSight, which is a lander that landed on Mars back in November of 2018. And that mission was going to study the interior of Mars. So it has a seismometer and it's listening for earthquakes on Mars, so Marsquakes. And I got to work on the instruments for that. And one of the things that was pretty neat is I was a payload systems engineer for that mission. And I was one of the primary interfaces for for one of the instruments, which was a French donated instrument. So I got to actually travel out to France a lot during that time, and it was pretty cool. You know, I moved to England and learned English in England, and that was kind of what opened the door for me in terms of a lot of these jobs. But it was really cool to sort of go back to my roots and say like, oh, you know, this language that I know, it's my first language, French, I got to use in my job, and you know, and exercise that to the benefit of my job. So that was pretty neat for me to be able to bring in some of those skills. But I mentioned that because often people ask me like, hey, you know, what kind of skills do you need in your job? And you know, there are the obvious ones, and math and physics and things like that. And I'll talk about some of the more important ones like communication and teamwork in a little bit. But remember that no journey is a straight path, and any skill that you pick up along the way, any interest that you pick up along the way, those are never lost. And you'll find that you'll end up using these weird skills you have in the strangest of times. And this was definitely one of those examples where I was uniquely qualified for that job just because of who I was and what my history was. And so now I work on the Perseverance rover, and Perseverance is just the latest in a series of rovers that JPL has landed on Mars. And I like to show this picture because really here, what I want to show is that we're standing on the shoulders of giants. So back in the 90s, there was a rover, a mission called Pathfinder and Sojourner that got landed, and that was the first little tiny rover that got landed on Mars. And then from there, we had the Mars Exploration Rovers, which are these two twin rovers that got landed in the early 2000s. They were solar-powered rovers that were meant to last 90 days, and they lasted about 15 years on Mars. And so they made some incredible discoveries at Mars, not only in terms of science, but also on how we operate a rover, how what it's like to drive a rover on the surface of another planet. And then in 2012, we landed the Curiosity rover. This is like a car-sized rover, again on 6 wheels, and it's still on Mars after 8 years. It's still, obviously they don't come back, but meaning it's still operational on Mars. And it was studying the history of water on Mars. It has an arm and a drill, and it's still doing science every day. So around after that time came Perseverance, and Perseverance is sort of the latest and greatest. It's the big sister, or the newest member of the family, and it resembles Curiosity a lot. We took that design and improved on it, and Perseverance is, among other things, also preparing for human exploration of Mars, and I'll talk about that a little bit too. So here's a CAD, you know, a rendered image of Perseverance. So to give you an idea, I always say that it's probably kind of like the size of a Mini Cooper, but then hike it up on 6 wheels, and all of those 6 wheels can individually drive, and then the front and back wheels can steer. So it's kind of a little bit of a monster truck in a way. The full height is a little bit taller than me. It's about 6.5 feet tall when you have the mast. And then this robotic arm here has 50 kilograms of instruments on the end of the arm, including a drill, a coring drill, some imagers, and other science instruments. The whole rover has about 10 instruments. It has 23 cameras and 2 microphones also. So for the first time on Mars, we'll be able to hear the sounds of Mars, hear the rover driving around. It even has a little laser in the eye here that can ablate rocks. If you ever play around with rocks, I don't know if you do, but I certainly do. If you've ever broken a rock open, the interior of the rock is usually a different color and a different composition than the outside, because the outside will get weathered from like rain and wind and things like that. So we have the same weathering process on Mars. So what that laser does, you know, in addition to being super cool because we get to zap rocks on Mars, it actually helps remove that top layer. And then that allows us to study the interior of those rocks. So speaking of, let me talk to you a little bit about why we're going to Mars. What are we going to be doing? Well, our rover is a geologist. We love rocks, and so we're going to be studying, you know, the history of Mars, the geology, and we're actually landing in a river delta. And I might show you that later, but basically we're landing in a place called Jezero Crater, which is obviously no longer a river. There is no liquid water on Mars anymore, but there used to be, we think, liquid water on Mars. And so Jezero Crater is actually an old lake bed that has an inflow and an outflow of a river, and we're landing in the delta. And if you know geography classes, from, I remember learning this actually in my year 9 geography class, that deltas on Earth are places that are very fertile, they're full of sediments, they're really, really interesting places to go. And so we think that that might be the same on Mars as well. But the main thing that we're doing is actually that we are looking for signs of ancient life on Mars. Ancient life, right? That's a big claim. But the story there is that Mars probably used to look like Earth about 2 billion years ago. There was a time when Mars had an atmosphere, it had liquid water, it had a magnetosphere. And so we think that maybe there might used to be life on Mars. Now, we're not talking like little green men walking around. That's not, that's not what we're looking at. But if you think about like 2 billion years ago on Earth, what Earth might have looked like, well, there was kind of bacteria, complex molecules, things like that. So that's what we're looking for on Mars is small, we call it astrobiology because it's biology outside of Earth, but small complex molecules that might have existed back then. But the coolest thing is that our drill is actually going to take samples from the surface of Mars, put them into tubes, and then eventually, this would be the first step into a mission to eventually bring those samples back to Earth, which is also a future mission that I hope to be involved with one day. And then finally, I mentioned that the rover is preparing for human exploration also. One of the things that it has on board is a set of instruments like a weather station. It also has a technology demonstration that will take a little bit of the Martian atmosphere. And remember, the Martian atmosphere is actually very thin. It's about a 1% of the Earth's atmosphere, but it's going to extract oxygen from the molecules in the Martian atmosphere to show that we can create oxygen from the resources that we have on Mars. That's called in situ resource utilization. But the idea there is that if this small technology demonstration is able to produce oxygen, then sometime in the future we could bring a bigger version of that to help our astronauts produce oxygen rather than having to bring it with them. So here's a little bit of an overview of what the timeline looks like. So we selected a landing site back in 2018. Actually, the mission itself started around 2012, 2013. It takes a long time for these complex systems to come together. It took about 6 years to build the rover, and I'll talk a little bit about that. And then we launched in late July of 2020. As I mentioned, we're on our way to Mars right now. We're about halfway to Mars, and we'll be landing actually right around this time, because it'll be about midday on February 18, 2021. So it'll be 8 p.m. for you in the UK, and there will be coverage of that, I'm sure. And then as soon as we land, actually we land wheels down and we'll be ready to go, and I'll be part of the team that will be helping out with surface operations. So I'm just going to show this video, and hopefully it's not too choppy. But what I wanted to show you is, part of my job has been to help build and test this rover prior to going to Mars. So I wanted to show you a little bit, what it looks like to build a rover, right? It's not something that we get to see every day. So I really like this video because it gives you context for all of the pieces. So this is the crew stage. This is sort of the housing. And then this is the descent stage for the rover. So this is the housing that the rover is in currently. So it's little shell that it's in on its way to Mars. What you're seeing here is us moving the rover from place to place around lab. The lab looks, a little bit like a campus, and it's not simple actually to move these things all around the lab. But you're seeing sort of the complexities of all the things that we have to build and assemble and test. And we do all sorts of tests. You saw some of our environmental tests. Here we're doing also some of the functional tests. And so what we do is we put the rover through all of the different environments. We shake it, we put it in a thermal chamber, mimic the thermal environment. We practice drilling, we practice moving things around, so that when we get to Mars, anything that we do on Mars, we've done with that vehicle on Earth first, and we know that we're ready to go once we get on the surface of Mars. Let me just skip to the next slide. And so my job specifically is that I'm a systems engineer, but I specifically work as part of the mobility team, which is kind of cool. I get to drive a rover on Mars. So my job is to make sure that the rover always knows where it's oriented and always knows, if I tell it to go forward, it goes forward, and the rover can also self-drive, which is pretty neat. So one of the biggest tests that we had on the flight vehicle before going to Mars was that we drove it once, at least, on Earth. And I will show you that right now. So this was one of the biggest tests that I was involved with, and it happened a little bit after my birthday last December. And I always find this kind of funny because there's 10 engineers watching us as we drive. We made a little obstacle course for the rover, and this is the actual rover that's on its way to Mars right now. And you see everyone carefully watching everything and being really, really careful. And the whole lab obviously came, but it's kind of like when you get the training wheels on when you first take the training wheels off of the rover, right, of your bike. So we're all watching very carefully, but the next time that this particular rover will actually drive is on Mars on its own, millions of miles away. But when you're the first thing, when you're doing things for the first time, you don't want to break anything. But it was a really fun test. We got to drive over a ramp. I always say we got to dance around, but we turned in different ways, made sure that everything was good to go. And so, that rover is now currently on its way to Mars, right? And we can't do any additional testing with it. So what are we up to right now, and what are we doing? And so one of the things that I've been busy doing is testing a lot of our software. And that we can do here with other replicas of the rover. And so we have two Earth replicas of our rover. One of them is Scarecrow here, which is a pared down version of the rover. And the reason why it looks like this is because it's actually a third of the mass of Perseverance. And we use it specifically to test mobility. And the reason why we do that is because Mars gravity is a third of the gravity of the gravity that there is on Earth. And so if you remember from your classes, force is mass times acceleration, and so acceleration can be gravity. So if my gravity is a third on Mars, then the force associated with, basically the weight of the rover is a third on Mars than it will be on Earth. So if we used the exact same replica to test things like traction, the weight on Earth would actually be a lot bigger, and so friction behaves differently, things like that. So since we can't change gravity, we change mass, we get it down to a third, so it has the same weight here on Earth as Perseverance will have on Mars. And that's the version of the rover that we use to do all of our mobility testing, put it through different types of terrains, and also test our autonomous navigation. But we have another version of the rover called Optimism, and this is one that I work with a lot, actually. And this is like the twin of Perseverance. And so it is exactly the same. The only difference is that it has a massive cable and we plug it into the wall, which is different from, the Perseverance has a radioactive source, and that's how we do our power. But my day-to-day, and especially the past couple of months, is I get to go work in the Mars Yard, which is this area you're seeing here, which is basically a big sandbox. And I drive this rover around and do a whole sorts of software testing and find any bugs, understand how we're going to operate this rover, so that, again, once we get to Mars in February, we're ready, we understand how everything works, and we can operate the real thing on Mars. So I mentioned earlier that, I had been an intern at JPL, so I like sharing this picture because here on the left is my first internship back in 2012. And that's when Curiosity, the older version of Perseverance, landed on Mars. And there was me in the Mars Yard, being kind of funny, but having the best time, seeing these things happen. And then now is me on the right, this is a picture that was taken last year. I get to be now part of the team that's putting that next rover on Mars, and that's really cool. But I always like to remind people that, for me, internships was the way that I discovered where I wanted to work and what kind of job I wanted to do. So, if you're at that part of your life, I would really encourage you to look for internship opportunities. And I've done internships all over the place. I worked for CubeSats down in Southampton, and that was like in-flight refueling. I worked for I did an internship for Bentley, the car company. I went out to India for a summer to work in microfinance research. I worked at different NASA centers, and actually all of those different experiences is how I found my home, and how I found, when I did this internship in 2012, I was like, oh, this is really what I want to do. So that's something that I really highly encourage, is look for internship opportunities and different ones so that you can figure out where your place is in the world. And finally, I mentioned earlier that one of the most important skills as an engineer is to be a good team worker. And the reason for that is because it takes a village to put these things together. And just wrap your mind around this. The Perseverance rover is so complex that there is not a single human on our team or anywhere on Earth that fully understands every single part of the rover. There just isn't. You could not build that on your own. It's too complex. And so when you work as an engineer, or, and that's true of a lot of STEM fields, you're really doing something that's greater than yourself. The reason why this mission exists and is on its way to Mars and is going to make these amazing scientific discoveries is not because of a single human. It's multiple humans coming together and building something greater than themselves. And that is such an incredible feeling, to think that, that is what us as humans, as a society, that's something that we can do. And I often tell people, like, yes, if you want to be an engineer, sure, math, physics is important, but let me tell you, being able to communicate, be a good team worker, and work well with others is just as important, if not more, than the math and the physics. I can teach you the math and physics. I can't teach you to be a good human and to be a good team worker. So, for those of you that are still in school and listening to this, I remember when I was in school thinking, like, oh, why the hell, why are they making me do these group projects? Like, I don't want to do this. I don't want to have to drag everyone else and do this team project. But as it turns out, these team projects are some of the most important, because they teach you those skills that are so essential in doing these history-changing missions and projects. So I'm going to leave a few resources here for you. If you want to learn more about Mars, about JPL, about NASA, or about me, I would check out all of those resources. But let's go ahead and take questions and have a chat about some of the things I talked about.
Thank you so much, Farah, for your thrilling story session and for all of your advice to everyone about going forward with this if they're interested in it. So we've had quite a few questions, and the first one we've got is, how long does it take for these to actually get to Mars?
So we launched on July 30th, and it's landing February 18, 2021. And so it takes about 7 months. It kind of depends on which launch opportunity we use. We can only launch to Mars every 2 years, but it's usually between 6 to 8 months. So in this case, it's about 7 months.
Wow. And so for far space missions to outer planets, what type of signals are used to communicate with the craft to make unplanned changes?
So that's a great question, actually, and let's get into that a little bit. So, so we talk to rovers or any mission going anywhere in space using radio waves. So same as, you might have your radio in your car. So it's a different wave. We don't have AM or FM. It's a different bandwidth. But it's, we call it X band, and we also have UHF, but they're just different frequencies of radio waves. Now, radio waves travel at the speed of light, right? They're just another type of electromagnetic wave, and they travel at the speed of light, which is incredibly fast. As fast as we can possibly go right now. But Mars is so far away, if you think about Mars, that on any given day when we talk to the rover, once it's on the surface of Mars, it takes anywhere between 7 to 12 minutes, depending on the time of year, for the signal to get all the way to Mars, and then it takes another 7 to 12 minutes for the signal to come back. And that gets even more true, like the further and further away we go. So, for example, when the astronauts went to the moon, the delay was only about 10 seconds, but Mars, you're talking 7 to 12 minutes. Once you go out to Jupiter or Saturn, you can be talking about dozens of minutes. So we try not to have unplanned events, right? We can't, if something was happening on Mars, and I was getting signals saying something's going wrong, that signal is already like 10 minutes old by the time it gets to me, and it's going to take, even if I react instantaneously right away, it's going to take 10 more minutes for it to get back. So we never do real-time operations. We can't because of that limitation. So the way that we operate rovers is that, or any mission, is that we have a lot of autonomy. The spacecraft have to know how to safe themselves, how to stay safe in the event of an anomaly, and that's how we deal with those things. So we pre-program everything. So on Mars, we'll send a plan for the rover to do every day when it wakes up on Mars, and then it does its own thing and then replies back to us at the end of the day with data and images. And then if it hits a hiccup, it knows itself, because of the autonomy that we build in, it knows to stop and call home and wait for us to tell it what to do next.
And so is it through those signals that you also know where it has landed on the planet and kind of what conditions it's in?
Yeah, so it's a combination of things. So on landing day, we'll be taking imagery as we're landing. We have a radar, so we'll have telemetry information from the rover that is going to be sent back through those signals, and we'll also have images from landing. But there are orbiters, and there are other spacecraft in orbit around Mars. And so those spacecraft will be tracking the rover when it's landing. So via the signals, it can track where it's going. And later down the line, we'll also be doing imagery of the site. So from orbit, you'll probably be able to see where the rover is. So that's how we figure out exactly where we are. It's going to take, usually on landing day, we roughly know within a few kilometers where we ended up just based on the data from the rover, and then we'll localize it more precisely after that. But the rover can also self-direct itself, and that's actually part of my job. It needs to know where it's pointed and where the Earth is, how to look, how to point towards us to send us the data. And it actually does that using the sun. So if you think of like the early explorers, they would use the stars, right, to direct themselves. Or if you ever go hiking, you can look at where the sun is, and based on the time of day where you're pointed. Am I pointing north or south? The rover does the exact same thing. It's just a little bit more accurate than just you eyeballing it. But it looks at where the sun is, and given the time of day, it then knows how it's pointed, and it knows where the Earth is based on that. So, so it's a combination of other information and then onboard autonomy.
And how much does it cost to have the rover and sending it out into space?
That is beyond what I know. I only really work on the engineering side of it, and these missions, the NASA missions, they're federally funded, so it comes out of the U.S. government budget. So it's a little bit above my pay grade.
So we've got quite a few questions about your beliefs related to the universe and other planets. So what areas of the universe do you believe in, given your knowledge in the domain? And do you believe in the superstring theory?
So I'm not familiar with the superstring theory, but I can tell you in general, like more generally, what I believe in. And, so obviously this mission is looking for life elsewhere on a different planet, and NASA really focuses on this concept of astrobiology and looking for life on other planets, not just in our solar system, but we're also looking at exoplanets. And so, a lot of time people ask me, well, do you believe there's life elsewhere? And I honestly do. It would be very hard to imagine, given, the expanse of the universe, that we're alone, and that would actually be very, very sad, I think, to me, if we were alone. And so, it's part of what we're trying to do is we are going to other planets and looking for evidence of life elsewhere. And and the reason why we do that is because we actually know that there are multiple planets out there that are habitable, that are in that Goldilocks zone, that kind of look like Earth, a little bit smaller, a little bit bigger, about the same environment. And there's an equation actually called the Drake equation, which defines the probability of there being life, intelligent life on other planets, and of us ever encountering life. But what that whole equation comes down to, if you look into it, is, it's a set of probabilities. Are there planets that look like us? How we evolved? What the probability of evolving? But what it comes down to is there do we even have evidence that there is life elsewhere? And if we can show that, if we find life anywhere outside of Earth, actually, that would show that the universe is probably teeming with life, and it's just up to us to find it. So, yeah, I really do think that there could have been life elsewhere. There might well still be life elsewhere than on Earth. I really sure hope that there is. And I think actually that we have a good chance of answering that question, within our lifetime, which would be pretty incredible to say that, like, to be part of. That's one of the reasons why I love my job, because I might be part of the team that helped find life elsewhere, like outside of Earth, and that has such huge implications in terms of our understanding of where we come from.
And so, linked to that, do you think that it would be possible for humans to live on Mars or somewhere else?
Yeah, so people always ask that question of, like, do you think humans could live there, or like, would you like to live on Mars? So let me tell you, it is very cold on Mars. So, a good day on Mars is about -40. You think English weather is bad, this is awful. And, overnight it will get even colder than that. And the temperature swings are intense, even between shadow and light, because there's no atmosphere. So I do believe that, we are working towards the human exploration of Mars. So I do believe that hopefully, again, in our lifetime, we'll see humans go to Mars and explore Mars and maybe set up, partial colonies. But I always remind people that planet Earth is pretty great. It takes care of us. It's reasonably nice to live here. So while I see ourselves, exploring other planets, we should always be looking at our planet first and taking care of our planet, because it's way better than anywhere else right now. That we know of, and I don't think that in our lifetime that we'll see people, moving in to other places. Planet Earth is so beautiful and so great, and we should be taking care of it.
And thinking back to the rover, how long does it take to build them? And also, do you have to use lots of different software programs for all the different functions?
So so in terms of building them, for Perseverance, we started around 2013-ish, so it took about 6-7 years to build. Now, we don't build everything from scratch. Anything that we can buy from other companies, we do. So we do, collaborate with other companies. The instruments are usually done by partners. So some of our instruments are Spanish and French, and then some come from other universities around the US. So we try and reuse as much of the available technology as we have, and then we build new things. So in the case of Perseverance, we started from the Curiosity design, so we didn't start from scratch. But one of the most complex things that we built, which actually took most of the time, is this sample caching system that was collecting the samples and putting the, that are going to collect the samples and put them in tubes and eventually leave them on the surface of Mars. And that was all brand new. And so it takes a while. In terms of software, I certainly use different types of software every day. The rover speaks one language, so it has its own type, software type that we use to communicate with it. It's essentially a language, right? And its own internal software that we also build in-house. But certainly, I've had to learn different types of software languages when interacting with a rover or doing the build and things like that.
And when you're communicating with the rover or it's being driven, is it, do you take it in turns, or is it one person? Is it as a group, or is it pre-programmed?
So it's teamwork. So it's a whole, it's a whole team of people. There's maybe 20 or 30 people just on the uplink room, and then there's another set of people that look at data. And the way it looks is that it's not in real time, as I explained. So what happens is we work during the Martian night, and then the rover works during the Martian day. And so, around 6 or 7 p.m. Martian time, the rover sends us all the information it has, all the pictures we took. There's a team that looks at all of that, establishes, okay, did everything happen as we expected? Is everything healthy? Do we need to fix anything? And then there is an uplink team that then prepares the plan for the next day, codes all that up. So each of us codes a different part of the activity. We bundle all of that together, and then we send that up to the rover before it wakes up in the morning. And my specific task is I work on the on the plan building side. And I'm one of the people that gathers all of those inputs together and helps all of the teams merge together and work together so that we get that plan and then send that up to the rover. So it's automated in the sense that we give the rover a plan and then it does what it does during the day. One little note though that's kind of interesting is we start on the same day and the same time on Mars every day, so around 6 p.m. Mars time, and we have to be done by about 6 a.m. Mars time. But a day on Mars is about 24.5 hours, so it's a little bit longer than an Earth day, which means that, time zone difference, say one day, if I'm starting 6 p.m. Mars time, it might be 9 a.m. LA time. Well, the next day, that's going to be 9:40. The next day, that's going to be 10:20. And then 11 a.m. and so on. So it makes it really hard when you're working what we call Mars time to actually plan a life, because on a Monday you might be starting at 9:40 and the next day, the next week you're starting in the afternoon and then the next week you're working through the night. So it's an interesting time when you're working with these rovers. We only do that for the first 3 months or so. And after that, what we do is we work every other day so that we can work sort of a reasonable set of hours.
And what is the next, as far as you're aware, what's the next most distant mission that is being planned by NASA? And is there much research going into shortening the time it takes to get to places?
So I'm going to be working on this Mars mission for a little while still, but there are certainly a lot of ongoing missions. I can't speak for NASA as a whole, but with JPL, one of the cool missions that are upcoming and the one that's going probably the furthest away is the Europa Clipper mission. So that is an orbiter mission that's going to go out to Jupiter, and I think is launching in a few years. And it's going to take a few years to get there also. And then they are also working on a mission called Psyche, which is a mission to a metal asteroid that's launching in a couple of years. It's a little bit closer, but not quite as far as Jupiter, but still pretty far away. So those are the two big missions that I know that are ongoing. In addition to, JPL also does Earth observing missions, right? So there's actually one that launches in a few weeks. So we look at our own planet as well and study what weather patterns, water patterns, things like that, carbon dioxide patterns. So we are one of the prime places that studies Earth's climate and studies the effects of climate change as well. In terms of finding ways to get places faster, absolutely. That's kind of one of the challenges of space exploration, is that it takes so long. So there's different ways you can do that. There's a whole field called mission design, which looks at different ways to get places based on different types of propulsion system. And that would be the subject of a whole other talk if we got into how that works. But certainly there are fields of research that look into this.
Where do you see yourself in 10 years, personally and professionally?
Oh, so I love being at JPL. I don't think anyone else, we are the only institution so far that has successfully landed something on Mars. That might change because, the Chinese launched a mission this year and the Europeans are launching a mission in 2 years to go to Mars. But for now, this is the only place where I can do what I do. So I think I may stay here for a little while if they'll have me. I will be working on Perseverance for at least another year or two. And then I hope that if Perseverance is successful, then the Mars Sample Return Campaign, which will be the campaign to go get those samples and bring them back to Earth, will kick off in earnest. It's currently sort of in the study phase and beginning to form, but we're really waiting to have those samples. So I would actually really love to participate in that mission. And, the timelines of these things are really long. And so if I end up on that project, I'd be looking at another 5-6 years of working for that. And we're currently projecting that if all goes well and we get the funding the way we want to and find the samples that we really want, that we would be getting those samples back about 10 years from now. So hopefully I'd like to be part of that team that brings the first samples back from another planet to Earth. And that's going to generate so much science, irregardless of all of the work that we're doing in astrobiology. Bringing samples back to Earth is important to us because when we go to Mars, there's only so many instruments we can bring with us. And so, we start up with a set of hypotheses, the same way as you do as a good scientist. We take instruments that we think are going to answer those questions, Then we get to Mars, and every single time we go anywhere, we end up with more questions and answers. And so we'll end up with a new set of questions. And we're stuck with the instruments we have. And so being able to bring samples back to Earth will probably enable decades of science, because as we answer questions, we'll be able to not only go get new instruments, but we'll be able to build new instruments, invent new things to measure the things that we're seeing. So that's going to be, from a science point of view, a pretty incredible time.
And finally, are you aware of how many other Ismailis are working in the space astronomy field?
I don't know for sure. I do know a few. Within JPL, there's 1 or 2, and then within NASA, I know, I've given a few talks recently, and so people have reached out. So I think there are a few, a little bit everywhere. I actually met someone who works at headquarters over in DC, and I'd invited me over. She works in the outreach department, and invited me over for a talk, and we realized from our last names that we're both Ismailis. So there are definitely a few out there. But I don't know for sure how many. So yeah, I would encourage you, if you have, if this piqued your interest, to go check out some of these sites, and then mark February 18 in your calendar. There will definitely be a live stream on NASA TV and on YouTube of the landing. So it'll be quite an exciting time. It's kind of the riskiest part of the mission, so we'll definitely all be very stressed out and on edge. But if we're successful, we expect to get the first image from wherever we're landing on Mars around 9 p.m. your time on that day. So yeah, if you have the time, check it out. It'll be a pretty momentous event.
Thank you so much, Farah. We've had a couple of people saying just how much of an inspiration you are, and we've thoroughly enjoyed your talk today. Thank you so much for sharing everything that you have shared with us.
Absolutely. Thank you for having me.
We've loved it. Thank you everybody for joining us as well. We really hope that you have enjoyed the session.